So actually, once you radiate it, like suppose we had radiated any kind of antenna placement yesterday. Actually, I did not run that particular simulation yesterday, so radiation pattern has not been. So once you run that, for example, this 3D pattern, if I want to export it to EMIT directly, like how the far field scenario is overall. So that far field data, if I need to export here, and I need to incorporate in EMIT then. So in that particular case, you can just click on that particular, for example, if you would have given it as infinite sphere there. So that 360-degree overall on the spherical, based on spherical coordinates would have been given that. So for that you can go to compute antenna parameters. In that you can see an option export field option. So once you click on export field, the far field data will be exported here, and you can just, for example, you can save it in some name like SBR plus or something, SBR CSV is anywhere you can save that. Okay, actually this has not run, and it has not been radiation has not been generated, so it is not been saved. So basically we used to save the far field data in this way, and let's suppose if we are going for EMIT here, to support this, let us start with the insertion of new EMIT design. Okay. So you can go to project, you can see an option insert EMIT design. So just you can give it over here. Once you click on this particular case of insert EMIT, this layout will be coming, and under the same project you can see EMIT design will be incorporated here. So now let's suppose we are kind of taking an pattern which we had generated in SBR plus. Okay, like an antenna I had placed on a pole kind of a scenario. Okay, so for that, first I'll insert an antenna, a schematic. You can drag and drop this, double click on this. So once you double click on that particular antenna, it will ask for where it has to be positioned. Okay, so once you come here, you can before this, based on your problem size or based on your electrical size, let's suppose whatever the problem which we had dealt, it was in meters. Okay, you can go to modular. Tools option, general option, in this default unit you change it to meter scale. Meter or kilometer you can keep, just we will keep as meters, then click on OK. Now once you double click on this, whatever the unit is, it will be in meters. You can mention where it was placed in that particular scenario. Okay, so let's suppose it was along, let us keep that particular center antenna was the pole or the antenna which was kept was that along X and Y it is 0, and only along Z, let's suppose it was some.
This sphere depicts like
the antenna, like the radiation pattern
radiation
of that.
pattern. It's an isotropic antenna.
Yeah. Now we hadn't assigned any kind of antenna, just we are positioning it where it needs to be positioned exactly. Let's suppose in that SBR plus simulation it was around the pole height, if it is around somewhat 200 meters, 100 meters or something. Let's suppose we have an around 50 meters, we'll keep it. So 50 it will be the height of it, so it will be placed here. And then the next thing is, let us introduce our antenna here. So either you can go for any kind of antennas which is present in the library, or else you can choose by file option. Once you choose by file option, you can import that far field radiation pattern here directly.
That's enough, like far field is enough or?
Yeah, far field is enough here. We need not to what the thing is, like whatever the far field radiation we are getting out, that is a kind of scattered radiation, or that is based on the external environment. So you can go to antenna file here, SBR plus far field. This is the older file which we had already generated. I had kept it. So once we click on open,
We can't give fixed select or something like that.
actually that option, it's GUI is pretty much new. They had not introduced it.
No. So you have to do it by manually.
Yeah.
this kind of thing.
You have to zoom in. Actually, if we see it as it is,
So is there any shortcut keys for the orientation, like the face?
actually in HFSS we have Control D.
Control D to make it center, like fit selector, right?
So actually it has been placed along Z. Okay. So now the thing is, like, I wanted to showcase this particular, the orientation in which particular direction it will be. So in this case you can change the orientation here in each and every particular angle. If you give that degree, the maximum based on like along the Z direction how it is, you can change the orientation of the pattern here. So once this is done, you can click on OK. Now your antenna has been defined here. Okay. So this is the antenna. Let's suppose this is a base station antenna.
So this you have designed in like where? EMD design you take, no?
What?
This one is like EMT layout, right?
This is EMIT layout. Okay. So what we'll be doing here is we'll be defining our RF system here. The antenna model, it will be from HFSS. The RF system we will be defining here. For example, in our case, let us go for this is the antenna which we have placed. Now we are going for RF system here. Either you can go for, if you are designing for any particular applications, these are library files, or else let's suppose if you are going for a new kind of radio based on your antenna design, you want to analyze. Okay. So in that particular case, you can insert new radio. Once you double click it, it will ask for the frequency band and the number of harmonics, how many it should be generated. So let's suppose in our case we kept it as somewhere around 28 gigahertz. So I'll keep from 27 to 29 gigahertz. Just for an example, I'm doing this. So 27 to 29 gigahertz, and the channel spacing 0.02. Modulation I am keeping it as generic. Either you can choose your modulation scheme, which modulation scheme you want to go. So once this has been set, then I need to go for transmission spectrum. So in particular transmission spectrum, how the band should be? Is it a broadband, or in both you have to consider narrow and broadband? And then what is the maximum peak power which we had got? So this we will get it out from the radiation pattern which we are getting. Okay.
So it automatically, like, we have to use that power now.
If you want to analyze your system, basically whatever you had used in that particular case, but for a 5G defined, there are certain limits which we need to address it. So let's suppose we had got for a single element we got around 7 dB, and for array what we had generated, it was around 19 dB or 19 to 20 dB. So I'll keep the gain as 20 dB. and this noise ratios I am keeping as minus 174, and the number of harmonics which you have to generate for each and every 27 or 28 gigahertz, the harmonics 10 harmonics will be generated, like till the 10th harmonics it will be there. So in my case, let's suppose we'll have only 2. So these only the base frequency and the first order I will be taking care. Okay, so once we click on OK, sorry, we didn't define the reception spectrum here. So the same way for reception spectrum, what should be the minimum receiving power? Like nothing, it is kind of
Sensitivity,
what is the sensitivity of it, and signal to noise ratio, how much it is, that we will be defining here. Okay, so this is how we will be defining a radio. For each and every case, there will be a different set of radios we will be creating. If you have a multi-band, so you have to create another band for the same antenna, or if you have a broadband, so based on that you have to create a different kind of scenario. So in this itself,
So is it possible to connect 2 radios with a single antenna?
no need of connecting 2 radios basically, because whatever the band of frequency if you want to go, let's suppose if you want to introduce a new band, add band, you can go here. The second band you can add it over here. So how many number of bands if you are going also, that it can be done.
Okay. And the same radio.
Yeah. The same if you want to go for add narrowband emission, so you can add your spectrum here. Like once you give here, it will ask for the bandwidth here. You can mention the bandwidth in that particular frequency range, which particular emission mask you have to. Like in stop band, we will be setting a cutoff frequency, like how we see the bandwidth here. So the same kind of customs, either the narrowband emission mask could be incorporated, or the custom transmission harmonics. The next harmonics, how much it should be. Okay, so based on this, like you can add that particular row or the band which you want to address it. So all these kinds of inclusions you have in transmission as well as reception spectra as well. So once you had built this, okay, the same way you can build the receiver antennas. Like you can keep another antenna there and you can receive it. So for example, this is a simple model which we are exporting. Similar way, I'll show you an example which we have directly here. So one is this Apache co-site in fighter jet, how we place, and based on that what is the co-site and other things, will RF interference, how it is. We'll see. We'll take a simple example of a mobile phone here. That will be easy to understand, so that in future case it will be better to, if you are going for your design, it will be better. So what we had did here is, we had modeled this HFSS design here, basically. So overall it is a kind of an how we design our HFSS model. The same way we had designed the overall system here. Like we had used a PCB basically and mechanical CAD modeling. We had done this and we had extracted the S parameter from this. So from this you can see we had extracted all the S parameters here. So for each and every case, we will be extracting the S parameters, and that we will be coupling it in this particular, that model we used to couple here. So actually we have a coupling, I forgot. So once you go to add coupling, this coupling is already added. So once you go to add coupling, here you will be getting an coupling designer here. Okay.
So why we are going for this coupling?
To take the environmental costs. Like let's suppose to actually it gives the path loss of it. Based on distance. For example, you are analyzing it for any kind of forest areas. So there will be certain scenarios where the coupling coefficient or the city-based model or based on trees, how the propagation constant will be decaying, the way of how it is getting decayed.
So
So
we are
those
coupling the
constants.
environment with the antenna.
Mhm.
We are coupling the environment with the
Yeah,
antenna.
and environment factors. Like it won't be an exact scenario, but general scenarios it will take. Like heights might be of this particular case, where, for an example, they would have made an interpretation like if a wave at 2.4 gigahertz or that certain particular frequency is going on and hitting a tree, how much loss it will be happening, path loss, how much it is. So all these patterns will be
So
going.
models will be there, no log periodic
The same thing. So you can see here, once you go to coupling here, you can see the S matrix coupling is nothing but the HFSS model S matrix will be importing here. Based on that, the whole models based on the reflection and transmission coefficient, it will be giving us what will be the overall scenario. This is for PCB kind of simulations we will basically use. So then the custom coupling here, we will be mentioning like what will be the antenna A and what will be, and based on SPR plus design, whatever we take out, like whole scenario we'll be doing it in SPR plus. We won't consider any other path loss. Whatever the radiation pattern has got it has got disturbed because of the environment which we had created. Based on that, we'll go here. So similarly, we have different types of coupling here. This is considering the path loss. Let's suppose you had just placed an single element or pole and an antenna, but you had just taken that particular parameter only. You had not considered the whole environment there. Okay, so in that particular case, what should be the path loss in an ideal condition? Here there won't any be based on distance, how it will be decaying. So that particular case we will take care. Like for example, if a pole antenna radiation pattern I had fixed at let's suppose from a distance it is around 5 kilometers. So what will be the path loss for 5 kilometers for that particular frequency of signal? That will be considered, and how the linking will be happening. So basically the signal strength, how it will be only based on ideal conditions, not any kind of disturbances we are not creating there. The same way, this is both are similar actually, two-ray path coupling and path loss coupling. Then log distance for very much longer ranges. It should be, we have these three cases are like there is no distance criteria. Like we can keep within 100 meters or something. But this particular log distance coupling, minimum distance is like it should be away from the base station antenna, or the linking of linking of antenna should have a distance of minimum some meters. It will just we will get to know. If I give for example this. If I keep urban or free space, let's keep it as free space. Actually, I didn't create model here. It will tell the distance. It should be minimal distance away from that. Whenever we create the radiation pattern or antenna in that place, it will ask for the distance. So based on that, this will be created. Other than that, we have HATA coupling for 5G simulations, where buildings and all these scenarios will be taken care. Then wall-fish coupling is a kind of reflections, based on the reflections, multiple reflections, how it comes. And this is a kind of an let's suppose I can say forest kind of scenario, where we will be placing an antenna in any kind of animals or other things to trace it out.
Okay.
So if we are going for those kind of applications, so there we can go for this particular cage coupling, and this indoor propagation for interior scenarios we can keep that, and 5G channel modeling for where you can go for only the link budget analysis. Basically we go with this particular case. Okay, so these are different types of coupling here. So in this case we had modeled here. So these particular S matrix we are coupling here directly with the EMIT model. So you can see we had created a GPS antenna and we had linked the S parameter here. Then the GPS receiver we had made it. So here you can see the band here, which is the first band of frequency, and channel spacing as well as the modulation scheme is PSK, and what will be the channel width here. So this will be only a receiver antenna. This won't be a transmitter antenna. Whatever the GPS antennas placed in a mobile, it will be only a receiver antenna. So we had disabled the transmission spectrum here. Only reception spectrum we had kept. The minimum receiving power and the SNR, all these values we had given. Similarly, there is another band of frequency, which is the second band, which is nearly at 1.2 gigahertz. Okay, so for that again we are giving the reception spectrum. Okay, so similarly for Wi-Fi we had created an around 2.4 gigahertz we had created it. So here you can see for 2.412, one is there, and then this is the reception. Actually we had created two bands here. The same band it is, but we had created just enable the transmission spectra here in the first transmission band, and for reception we had created again. So the same case, for the same band we will be having a reception criteria. Now the next thing comes is when it comes to mobile antennas or GSM or network antennas. If it comes in that particular case, we need it is a kind of a trans receiver. In this GPS it is only a receiver antenna. In Wi-Fi it is only a transmitter antenna.
So both transmission and reception is possible.
Like for hotspot kind of things, it's only a kind of transmitter antenna. It's not a receiver. So we had kept that particular case here. We had not included the receiver part. Yeah. So in this case you can see.
But you are checking the receiver side inside the radio.
It's just expecting one scenario that
either it is receiving or transmitting it.
Okay, at a time.
But in GSM it's a kind of an trans receiver here. Okay, so here we will be having all kinds of 850, 900 and 1.9 gigahertz. So for all these cases we had set the band, and in this we had enabled the transmission spectrum. The same way for reception spectrum, reception band, we have the same kind of, just either we can enable both at the same time, but sometimes it shoots some error. Like for this case, the sensitivity, the reception selectivity and sensitivity will be a problem when I go for like band notch. So because of that, we are creating the bands separately for transmission and reception. So you can see different types of bands here. Basically this is nothing but you want to incorporate or you want to get the data of your antennas, and you have to put it here, the far field. Either you can go for far field data, or using S matrix you can couple it here. Once you had coupled, you need to create an RF system. So then once you created an RF system, let's suppose we'll just run this simulation and see. Okay, so we'll just analyze this. So now first we'll start with the RF interference analysis. What it basically does is it will see for the interference between each and every antenna. Okay, so it will look like the whole spectrum will look like this. Okay, so you will be getting an antenna matrix here. So once you run this, okay, now you can see whichever is green here, that doesn't link with either antennas. Okay, I'll just reduce the resolution. that all the boxes will be clear here.
Lowest.
Should be fine, I think. So now you can see this is my transmission and the reception matrix here. So here my Wi-Fi antenna is a transmitter and GPS is a receiver. As we don't have any frequency coupling here, okay, you can see this is at 1.4 or something GPS reception band is. If you want to see that particular band also, you can just see which is the transmission and which is the reception band. Okay, so you can see it over here, and you can set the EMI margin also in this case. So for example, if you go to this EMI margin, based on your system which you are working on, let's suppose if you are going for automotive industry, there is a set of EMI margin limits which has been kept. So for aerospace it is different. So you can set your separate EMI margin, and that will define the maximum limit here. If it goes above the EMI margin also, there will be interference happening. So let's suppose this is it shows the linking, whether the linking is happening or not. Okay, so from Wi-Fi the linking with GPS is not happening. Then with GSM, GPS is not linking. So GPS antenna is not linking or doesn't have any kind of interference. But the only thing is like it is trying to go beyond the EMI margin sometimes. Okay, so that is being considered here. Then the next step is the Wi-Fi antenna and GPS GSM antennas. So you can see here clearly. The first thing is it is crossing the limit, the maximum EMI margin also, and it is directly linking with that is GSM antennas. Wi-Fi antennas 2.4 gigahertz. So because of that, there is a linking happening here. So this particular margin, you can say this is the EMI margin which we had kept. So if it cross beyond that, again there will be interference happening. So because of that, these two cases the interference is happening there. The same way again with USB is nothing but the transmission lines also sometimes it might dissipate. So considering that, we had kept an USB memory space kind of an area, which is not basically an antenna but an RF system which we use there. Okay, so if it is trying to couple with that also, as it is pretty much near field to it, nearer to it, so so we will be using this particular case. Okay, so once this is done, the next thing is we will be analyzing all these data, and we can set the EMI margin, or by problem if you want to make it out, all receiving in channels or out of channel if something is going out of channel, or harmonic if you want to go off. So all these inputs you can give it out here. Okay, so
என்ன ஒர்க் ஷாப் எதுக்குங்க இதை ஒர்க் ஷாப்
ಇದು 5 ನಿಮಿಷ. So basically, let's suppose we got to know we had received some kind of harmonics here. Okay, so the next thing is we need to suppress those harmonics. Okay, so in that particular case, what we can do here is we can go into this particular EMIT model. Let's suppose the GSM and the Wi-Fi antenna is kind of interference is happening. So what you can do here is you can incorporate a kind of filter here. Whenever it is transmitting at 2.4 gigahertz, it will suppress that particular wave. Okay, so let's suppose we'll go for a filter here, band stop filter basically. So that we'll keep it over here, and we'll connect it and we'll define the filter what should be the band here. Okay, for example, in our case,
2.4.
it is around 2.412 or something.
4 to 7.
I'll just keep it as lower cutoff 2.4 and that's all. Let it be 2.8. Cutoff at
You have to change it.
cutoff
Here will be
The band is
2.4.
top now.
2 point. I'll keep it as 2.22. Their higher band stop will be 2.52.
Right.
Here stop.
But it will take band pass.
No, band pass.
You just set a lower
So
cutoff and higher
low cutoff and higher cutoff.
That is enough.
Lower cutoff is 2.25.
No, higher cutoff 2.5.
Higher cutoff
That is
is
enough.
2.2.
You check it.
Yeah, okay.
Huh?
This one.
In between that we will see
Yeah.
And let's suppose I need to suppress it attenuation 40 dB. So once we simulate this, the coupling is there. So I need to, in this particular case, the 40 dB suppression, it is not enough. So I need to more suppression there. Okay, so in this case, we need to make it
ನೀವು ನೀವು
Actually, this in this particular case on first band itself, it is crossing the EMI margin. So it is again we need to suppress this 20 dB or something here. Okay.
So now
this
second
has
band
been
is switched.
decoupled here.
Okay.
The second harmonics has been decoupled, but still this is crossing the EMI margin. Because of that, the linking is again here. So here you can set two stop bands, another filter which will be taking care of this particular EMI margin. Okay. So basically, this is how we will go with. Again, if you want to make with any kind of other things also, you can use this schematics like divider or something. If you want to add it over here, you can play around with your circuit. Like only the antenna model you will be taking it from HFSS, and all other schematic implements. In your case, sir, you can design these kinds of filters.
Already designed, we can input here.
Actually, for antenna filter, we don't have any kind of import option here as of now. Only with antenna far field we can do that, because basically this is for RF interference. So we'll have a small break. We'll just wind it up like 5 to 10 minutes. We'll come back. So we started too late actually. We won't be able to cover all the topics.